So we're given a function, and it's defined on the whole real line, and it has a very specific property that whenever we take two outputs, the difference between the outputs will always be less than or equal to the square of the difference of the inputs. And from all of this, we're supposed to show that our function f must be a constant function. Now, if you think about it, if our function were constant, then this thing over here would always be 0, because those two outputs would be the same. And of course, that would be true. But this is asking us to show that that's the only way that this thing can happen. So how could we do that? How could we ever show that a function is constant? Well, it helps a little bit to know that this problem comes up in a real analysis course where you would be learning about derivatives. And there's a really wonderful fact that follows from the mean value theorem, which says that if a function has derivative 0 for all x, in this case in the domain the real numbers, then f is constant. And so what our goal in this problem is going to be is to show that our function is indeed differentiable and the derivative at every point is going to be 0. So we're going to show that f prime of a is 0 for every a in the real numbers. And so let's do that. And so the way our proof is going to go is we're going to let a be some arbitrary real number, and eventually we're going to calculate the different limit of a difference quotient to kind of calculate the derivative by the definition. But before we do that, we have to do a little bit of exploring. And so I'll move these around in a little bit, but we're going to have to consider this difference here divided by this difference here. So the limit as x approaches a, that's going to be the derivative if it exists. And what we have to do is we have to figure out how we're going to calculate that limit, given that the only thing we know about our function is that inequality up there. And so what I'm going to do is I'm going to take that inequality and I'm going to rewrite it. So from the given inequality, if I divide both sides by x minus y, in fact, let's divide both sides by x minus y squared. I think it's a little bit easier. Then we're going to notice immediately that for any x and y, if we divide, and I've replaced the parentheses with absolute values, that's okay, that this fraction is always going to be less than or equal to 1. And this is true for all x and y in the real numbers. So no matter what I do, that quantity there is going to be guaranteed to be less than or equal to 1. And so now, for my problem down here, well, I notice that I very nearly have that expression. And so if I take this and I were to, I don't know, take the absolute value of it, well, that is going to be the absolute value of f of x minus f of a divided by the absolute value of x minus a. And if I wanted to kind of get it exactly like the expression above, I would have to multiply by x minus a over x minus a, just those absolute values are going to cancel out. And now I can use we'll call it the red star. So now from the red star, I can conclude that this is going to be less than or equal to the absolute value of x minus a. And so now I have a really beautiful fact that if I take the original thing inside my absolute values, which is this difference quotient, so that thing here, which I'll emphasize is this purple thing, if the absolute value of the purple thing is less than some positive number, x minus a absolute value, then that purple thing, that thing inside of the absolute values, has to be between the positive number and the negative number associated to it. So we have this fraction squeezed between two values. And if you've noticed, I use the word squeeze. That's not a coincidence, because now by the squeeze theorem, put a period there, so by the squeeze theorem, if I take the limit as x approaches a, the limits of the outermost things are just 0, right? As x approaches a, as a function of x, those are continuous functions. We can just evaluate at a, we get 0. So the squeeze theorem says if you're squeezed between two things that are both going to 0 as we take a limit, then our limit in the middle also has to be 0. And that, finally, is the definition of the derivative. So we can conclude that our function indeed has a derivative at a, and that derivative is equal to 0. And if we zoom out just a little bit, that was our goal, and that completes the proof using the fact that we had at the top. I love this problem because it's not too complicated, but it does use some cool facts like the mean value theorem to prove that fact at the top, to recognize that 0 derivative gives you a constant function, and some cool inequalities and absolute values in the middle as well. So let me know what you think. If you have questions, put your thoughts in the comments. And if you like this, please consider liking the video and subscribing to the channel. I'll try to post more content based on what people want to see. Thanks.